Let's start our discussion of method-level refactoring. And remember that refactoring is now something that you're going to be using in at least two different ways, right? When you're dealing with legacy code, once you have some test coverage, refactoring is often necessary to get to the point where you can make the extension you need. Very often what you find is that you've got your test coverage in place, you have a reasonable understanding of the methods you need to change, but the method is structured in such a way, or the methods are structured in such a way, that making the change you want can't be done cleanly, right? What you're trying to do is essentially expose a seam where you can change what the actual code is going to do. And if the seam you need isn't present, you need to get it into the right place, and refactoring roughly is how you do that. So the idea is that you're going to start with code that has one or more problems or exhibits one or more smells. You already were exposed to some of the smells. We'll talk about a couple more. And in this case, the problem that we're going to say the code has is we know what we want to modify about it, but we don't necessarily have a clean place where we can make those changes. So through a series of small steps, you'll transform the code into a new version that has the same behavior, but from which the smells are absent, or where you've exposed the necessary change point. And you protect each step with the tests you already have or the tests that you create along the way. And your goal is to sort of minimize the amount of time during which tests are failing, right? It's an inevitable consequence of this idea that as soon as you make a change, something is likely to fail. So the idea is just to minimize the amount of time that happens, create tests as you go, and fix the tests that are broken because they rely on something about the code structure that you have now changed through your refactoring. Refactoring has, I think by this point, a fairly illustrative history. I think many people would agree that Martin Fowler and his colleagues who are part of the Agile movement developed what most people now think of as kind of the definitive catalog of refactorings. And the original book was just called Refactoring. The examples, I think, are in C++. I don't even remember. But since then, they've come out with different editions of the book that are focused on different languages. And it's actually useful in this case to look at the different versions, because there are some refactorings that, depending on the language you're using, don't actually buy you anything. They're not needed in every language. But the book really does read like a catalog. It's like a recipe book. For each refactoring, Fowler tells you what's the name of the refactoring, and the name is usually supposed to describe what the refactoring does, like extract a class, decompose a conditional. There's a sort of short summary of what it does, kind of in plain English, and when you might want to use it. What problem does it solve in your code? Like what code smell or what anti-pattern does it help you with? And then there's like a recipe, like a step-by-step procedure that you can follow to actually do the refactoring, and usually there's an example accompanying. So the book tends to be pretty thick because there's dozens and dozens of refactorings. But we're going to explore the context of one particular example, which is a piece of code that, for an unfortunate day in 2008, turned this into that. This was the then infamous Zune bug that if you powered up your Zune on the last day of 2008, it would brick. And the only way to unbrick it was to wait until January 1st, 2009 and power cycle it. There was no fix. Like hardware, nothing would work. So we will use a simplified version of the code that had that bug as the motivation for some of the refactorings. And you've seen some of this code before, because when we talked about, let me find, here we go. When Dave talked about code smells and metrics a while ago, this is basically a transliteration from Java of the offending code that caused this problem. And we're going to go about doing a few refactorings to fix this. So part of refactoring is one of these. It's a little bit like riding a bike, right? There's this big catalog of refactorings, and if you haven't dealt with bad code, you're sort of looking through the catalog. It's not clear which ones you should apply. This is one of those things where as soon as you start doing it, you get better at it fast. So don't assume that I've memorized the entire catalog of refactorings, but there are a few that come up over and over again. And some of them are immediately revealed when you use tools like Reek or Flog to analyze your code, and you get some hints about where the problems are. So if you remember back to when Dave used this example in class, one of the design smells or code smells that was pointed out is uncommunicative variable names, like D and Y. And most people, looking at this code and seeing constants like 365, that might tip you off that this has something to do with date manipulation, and Y, 1980, that's a year. So one thing we could do, and kind of low-hanging fruit, is we could just fix stupid variable names. Let's just assume we're right, and we'll fix the variable names and say, OK, we're going to assume this is about days and years. We haven't changed anything except the variable names at this point. So this is arguably on its way to being a little bit better, because now at least the variable names are trying to tell us something about what we think the code is going to do. The next refactoring that we apply to this one is extracting a method. So one of the problems with this long method here is that it's long, right? It's convoluted. It's got this nested conditional in it. So one thing that you can do when you have a method that's got this problem is essentially look for little methods that you can pull out and just call them by themselves. And a nice side effect of doing that is it isolates a piece of code and makes you think about what that piece of code is trying to do. Our example of that in this case is, let me compare the two side by side so you can see here. Again, using our technique of deduction, you might recognize this as the rule that allows you to calculate if something is a leap year. So we could, this very simplest thing we can think of is let's just take this conditional and let's factor it out into its own method. Right? So all I've done is replace it, but in some sense the code already becomes a little bit more readable because now I'm starting to pick variable names in a narrative that convey intent. So where I'm going with this is, if you think about what makes a good newspaper article, the first paragraph gives you a high-level view of what the article is about. Right? If you remember in high school, there's like the who, what, where, when, and why. And then if you're interested, after the first paragraph, you start reading the subsequent paragraphs, and each chunk of paragraphs kind of goes into one more level of detail. So that's kind of how we would like our code to read. We would like the high-level description of this method to eventually be short enough that most of the work is actually being done by helper methods that we have extracted. So a first simple example is all we did is take the logic that used to be after this if, and we moved it down here. Now, of course, in the process of extracting the method, when the code was inline, we had a conditional after the if that directly looked at the value of year. Right? Let's just remind ourselves what's going on. This is what it used to look like. That means that if we're going to pull this stuff out into its own method, now we have to pass year to it as an argument. So this is kind of an example of something that happens with refactoring is you start understanding where the dependencies are. Right? So here's our method called convert, and here's another method called leap year that we're trying to extract, and they both have to talk to, they're both operating on this same temporary variable or instance variable. We're going to make it into an instance variable called year. So that kind of gives us a tip-off into our next refactoring, which is, well, this shouldn't really just be a method. I mean, if we're going to have a class, and we've got a method here that manipulates year, and a method we just tried to extract that also manipulates year, and the only way to communicate year between them is to pass it as an argument, this is something that should be telling you that this is a good place for an instance variable. Right? We have an attribute of the object that more than one method of the object needs to talk to. In fact, one of the metrics that I believe Dave mentioned was cohesion, which is basically, given these attributes and given this set of methods, is it the case that most methods really need most of the attributes? Because if the answer is no, if you've got one chunk of methods that only uses certain attributes and a different chunk of methods that uses a totally different set of attributes, maybe what you've got is two classes. Right? So here we're doing the opposite thing. We're saying we've got two methods that wish they could use the same variable, but the only way to do it is to pass it back and forth. So if we extract another method and we encapsulate the class, well, we already have a date calculator class. We just got to make these things instance variables. OK, so now we'll add a constructor to the class. And while we're at it, we'll make days an instance variable too, in case we need to pull it out somewhere else. So we now have to initialize it. Right? This is, again, one of the things that happens with refactoring is in changing the structure of code, you often change the way it's going to be used. The way the original version of the code was used is you would just call convert and you would pass it an argument. The way the new version of the code is being used, you first have to initialize it. So you have to create a new object and pass the argument to that, and then call convert as an instance method. Right? So why are we doing this? We're doing this so that we can start encapsulating the data that is shared across these different methods, keeping that data inside of the class. And we've also decomposed the conditional. Right? So again, let's look at the original code. What did the original code have? It had if complicated condition is true, then there's two different blocks of stuff. Here's one block of stuff. Here's the other block of stuff. So suppose we just apply the same technique of extracting the method to each of those two blocks of stuff. We're not going to touch the logic. We're not going to try to figure out if it's right or wrong or what it does. All we're going to do is move it from one place to another. So we're going to take these lines of code, move them into their own method. And we're going to take these lines of code in the else, move them into their own method. And we'll give them provocative names. Whoops, there we go. If we didn't understand what the methods did, we could give them names like method 1 and method 2. So in the interest of getting through a simple example in the time that we have, I will skip the step where it dawned on me that This logic that I just copied over, and by the way, notice that we made year into an instance variable, so I've changed it to use the instance variable. That's the only other change I made to the method. Otherwise, all I did was copy the code. Here's the first branch of the if, and here's the else branch of the if, right? So I didn't actually change any of the logic. I just changed what used to be local variables so that they're instance variables. That way, all the methods can see them. And I gave each method a name. And already, the narrative is starting to get better, right? This is, at a high level, this is what the method does. So once you get to a point where you say, aha, the logical flow of the method is beginning to emerge, right? I have a counter or something that keeps track of how many days have elapsed since this year. And if the current year is a leap year, then I'm going to peel a leap year off of my count. Otherwise, I'm going to peel a regular year off of my count, right? So where this function is going is, given a number of days since a magic date in 1980, what year is it now? That's what the function's actually trying to solve. In a minute, we're going to run the unmodified version of this. So we've extracted some methods. We've made some instance variables, which used to be regular variables. And now we can start adding some tests. If our assumptions are correct about what this is supposed to do, I created this little helper method called test leap year that basically just sets the origin year, right? So the default constructor here sets the origin year to 1980. But for the purposes of testing, I created this little helper function that allows me to reset that value. And I can actually test whether different years are leap years. So if my assumption is correct, I should be able to now write some simple tests that actually check if the leap year calculation is working correctly, right? I'm not going to run these tests here. You'll have to take my word for it that they work, because I want to get to the more interesting test that doesn't work. Because if we also want to test the other extracted methods, the add leap year method and the add regular method, well, what happens when you add a leap year to the count of something? If the idea is that we've got this counter of how many days there are, and the counter, basically, every time you're in a leap year, you want to subtract the leap year's worth of days off of the counter and increment the year by 1. If you're in a non-leap year and you've got at least a day's worth, you want to peel off a year's worth of the counter and then increment the year by 1. And if there's fewer than a year's worth of days left, then you don't want to do anything. So if I just take those statements and I try to capture them in specs, if I start out with a number of days that's less than any type of year, then reasonably I should expect that calling add leap year should not change the year variable. Conversely, if I start out with a number of days that is more than a year, and if I start out in a leap year, then I should expect adding leap year to change the year by 1. And here's a boundary case. And remember when we talked about unit testing, what makes a good unit test? Well, you want to try to test representative values sort of in either branch of a conditional, and then you want to try to test for the boundary value. What's the boundary value for a leap year? It's a year that has exactly 366 days, right? That's what a leap year is. So that would be a good value to try. And this is saying that if we have a leap year's worth of days left, and it happens to be a leap year, then I would expect add leap year to change year by 1. So these tests are more interesting to run, and I have conveniently set up 2 terminal windows here. This is a file that contains exactly the code that we saw here. So it's got both the code for the date calculator class and the code for these simple specs. And if we run them, one of them fails, right? So this is this is the transliterated code that you can find on the internet that was unfortunately in the shipping Zunes. So apparently our test case is failing here, that if exactly a year's worth of days left and it's a leap year, the result should have been changed by 1 but was changed by 0. So this is telling us that when there's exactly a leap year's worth of days left and it's a leap year, the function isn't doing the right thing. So we could look at the code and ask why add leap year is not doing the right thing. We could also do the following amusing test, which I've prepared solely to amuse you. I have computed how many days there are from January 1, 1980 to December 31, 2008. So here, let me change this to a different number so we can get... This is what it's supposed to do, right? If 10,590 days have passed and the origin is January 1, 1980, then the current year must be 2008. If I change it to this value, what happens? OK, I've now bricked my Ruby interpreter. So this is the unfortunate manifestation of the bug that actually happened, right? And if we go back to our failing test, that it should peel off a leap year if exactly 1 year's worth of days is left, and we ask, well, where is the bug? If exactly 1 year's worth of days is left, what does that mean? It's, we tried the boundary value of 366. That should have caused year to be incremented by 1. So clearly this code path wasn't followed. And after you think about it for a little while, you'll realize that there's an off by 1 error right there. Right? A leap year happens if you've got greater than or equal to 366 days remaining on the counter. And indeed, if we go back to our terminal window, and if I now, shall we redefine this method in place? No, let me get a version of it that I can cut and paste. OK, so here's the version that we were just looking at in Pastebin. I'm going to make one change. Boink. I will grab this whole class. I will copy and paste this class into the interpreter. And we will try rerunning. Whoops. And now we get the right thing. Or at least we don't get a brick. Not getting a brick is infinitely better than getting the wrong thing. And just to make sure, I'll save the entire file, and I'll go rerun the specs. And now the specs are all green. You will not always be so fortunate to encounter the bug during your 5-minute demonstration. Okay? Clearly, I did some research to make this work out the right way. But part of the moral of the story here is that as you're doing the refactoring, it helps you find these problems. In a nutshell, what we did is we started with the method on the left. And this was a transliteration into Ruby of the code in the Microsoft Zune that caused the infamous December 31st, 2008 bug. And what we ended up with was the code on the right. And we applied a number of different refactorings, which I'll review in just a moment, which are part of a much larger catalog of things you can do to clean up your code. But remember, the goal of refactoring is to improve the structure of your code without changing its behavior so that it becomes easier to read and presumably easier to maintain. So to that end, it's worth looking sort of qualitatively at the difference between these two. On the one hand, the code we started with, it's got nested conditionals. It's got a pretty complex control flow. Even though we initially started by trying to change the variable names to something more meaningful, it's a pretty high cognitive load for a programmer who didn't write this function to look at it and sort of try to figure out what the intention was of what the function does. On the other hand, if you look at the version we ended up with, basically, we've captured the logic of this function in a small number of lines. Right? We have a single while loop. And inside that while loop, there's only a single condition. And we've used helper methods to extract everything else. So we'd said that one of the things that makes good code is it reads like a newspaper story. The first time you look at the code, the first few lines, you can quickly get an idea of the intention of what the code is supposed to do. And as you sort of scroll down and you look at the helper methods, you can start seeing the details of how you do it. So this goes back to the SOFA guidelines. Remember, one of the SOFA guidelines is try to stick to a single level of abstraction within a single method. And indeed, you could argue that on the left-hand side we did that, but the level of abstraction is too low. On the right-hand side, this entire convert method really is in terms of what we want to do, not very much of how we want to do it. And then as we scroll down and we look at the helper methods, we can see that the helper methods get into more detail about how to do the individual things. So this is what you're shooting for in your code. The first couple of screenfuls of code really should make it clear what the intention is, what's the code trying to do, and then rely as much as possible on helper methods and on collaborator classes for the how you do it.